You know, there's this invisible rulebook that governs pretty much everything in our universe. And today, we're going to try to decode it. It's called thermodynamics. These are the fundamental laws that tell energy what it can and can't do, whether it's the steam in a power plant or the fire burning inside a star. I mean, have you ever actually stopped to wonder about that? It seems so simple, right? So obvious. But it actually points to this really deep truth about our reality. It's like energy has a preferred direction, a one-way street it always wants to travel down. And that's not just some random coincidence. It's a huge clue to how the universe really works. And yeah, the answers lie right there, in the laws of thermodynamics. Now, these aren't just some abstract, high-level physics concepts for a textbook. Nope, they explain the why behind so many things we see every single day. They literally define the boundaries of what is and what is not possible in our world. All right, so let's dive into the first rule. This one's the most famous one, and you can kind of think of it as the universe's ultimate accounting principle. The big takeaway? You can't get something from nothing. This is the famous law of energy conservation. Basically, every single bit of energy that exists in the universe today has been here since the very beginning, and it'll be here until the very end. It doesn't disappear. It changes its costume, moving from one form to another. So, okay, how does that actually happen? Well, let's say you add heat to a system. Think of the gas inside a cylinder. That energy has to go somewhere. It can do one of two things. It can either crank up the internal energy of all those little molecules, making them jiggle around faster, or it gets converted into useful work, like pushing a piston up. The point is, it never ever just vanishes. And hey, this isn't just theory, right? You've actually experienced this yourself. Think about a bicycle pump getting hot as you pump it up. That's the work you're doing turning into heat. Or just rubbing your hands together to get warm. That's you converting motion into warmth. It's the first law in action, literally in the palm of your hand. Okay, so if you can't win by creating energy out of thin air, can you at least break even? Can you get back all the useful energy you put into something? Well, I hate to break it to you, but the second law has some bad news on that front. See, this is where the two laws kind of work together as a team. The first law, it sets the limit. It says, hey, the total amount of energy is fixed. But the second law, it adds this really crucial twist. It sets the direction. It explains why your coffee cools down but never heats up on its own. It's what gives us what physicists call the arrow of time. So the big takeaway, the crucial point is this. There's basically a tax on every single energy transaction in the universe. Think about it. You can turn work perfectly into heat, like we said, rubbing your hands together. But you can never, and I mean never, turn all the heat from, say, a fire perfectly back into useful work. But why? It feels like it should be possible, doesn't it? Like, why can't we just be more clever, build a better, perfect engine? Well, the answer isn't about our engineering skills. It's about the fundamental nature of how energy itself flows. Okay, for an engine to do any work at all, it has to create a flow. It's got to take energy from a hot, concentrated source, right? It uses some of that to do its job, but, and this is the key part, it must dump the rest of it into a colder, less concentrated place. So that waste heat you feel coming off an engine, that's not a bug, it's a feature. It's a fundamental requirement. And this really shows you just how big this cosmic tax is. In your typical car engine, only about a quarter, just 25% of the energy you get from burning gasoline actually goes to moving the car forward. The other 75%, that's just dumped into the environment as useless waste heat through your radiator and exhaust. Crazy, right? And this right here, this gets to the very heart of the second law. It's the law of irreversibility. An ice cube will always melt in a warm room, but you will never, ever see a puddle of water just decide to freeze itself solid by making the room around it warmer. That one-way flow, that's the arrow of time we were talking about. So this whole one-way street for energy, it's actually just a symptom of something way bigger, a much more profound trend in the universe, this relentless march towards disorder. And that waste heat we keep talking about, it's just a form of disordered energy. And physicists have a special name for this idea, entropy. Now, I know entropy sounds like a scary, complicated word, but don't let it fool you. At its core, it's just a way of counting. It's counting all the different ways a system can be arranged. So the more disordered or random something is, the more possible ways there are to arrange it. And you guessed it, the higher its entropy. Here's a great way to think about it. Imagine a brand new deck of cards, fresh out of the box. It's in perfect order, right? Ace to king, all the suits together. That is a very low entropy state, because there's only one specific way for it to be in that perfect new deck order. Okay, so what happens next? You shuffle the deck. When you do that, you're basically mimicking a natural process. You're adding a little bit of random energy and just letting things rearrange themselves. And here is the absolute key insight. There are countless, trillions upon trillions of ways for those cards to be all mixed up and disordered. But there's still only one single way for them to be in that perfect new deck order. So you see, it's not that the universe wants chaos or anything. It's just that disorder is so much more likely, just based on pure probability. The universe is always shuffling the deck. And this brings us to the second law in its most epic, most profound form. The total disorder, the total entropy of a closed system, like our universe, is always increasing. Now you might think, but wait, I can create order. I can build a house. And you're right. You can create these little pockets of order. But the energy you spend, the mess you make to build that house, it always creates even more total disorder in the universe as a whole. So you see, these aren't just some dusty old rules for steam engines or chemistry labs. These laws are the fundamental operating system for our reality. They dictate everything. They tell us what can happen, and maybe even more importantly, what can't. So let's just quickly recap this cosmic rulebook we've been talking about. The first law, that tells us you can't win because you can't create energy from nothing. Then the second law comes in and says, and you can't even break even, because there's always that waste heat tax. And the reason for all this? It's entropy, the universe's unstoppable tendency to move towards its most likely state, which is disorder. And that leaves us with one final, kind of mind-bending question to chew on. If our universe is a closed system and its total disorder is always increasing, what does that mean for the far future? What happens when everything evens out, when all the energy becomes just one big, lukewarm, perfectly disordered soup of waste heat, when there's no more flow and no more work left to be done? Well, that is the ultimate thought experiment that the laws of thermodynamics leave us with.